Chapter 8, Systems of Equations, Section 8.4, Systems of Nonlinear Equations. We had previously looked at systems of linear equations in Section 8.1. We're now skipping to Section 8.4, but actually dealing with a very similar situation, the only difference here being that we're going to be dealing with systems of two equations and two unknowns where at least one of the two equations in the system is nonlinear. That is, it's not a linear equation. That would mean that its graph is not a straight line, and due to that fact there are different solution scenarios that we might encounter versus linear systems. So if a system of equations includes one or more equations that are not linear, the system is called nonlinear. Nonlinear systems can have no solution, as is the case with linear systems, one solution. Again, linear systems can have just one solution. But then there's a possibility of two solutions or three solutions, depending on the number of points of intersection of the graphs of the equations. You keep in mind, with a linear system, there are really only three possibilities. You can have no solution, one solution, or infinitely many solutions, because both of the equations in the system will have graphs that are straight lines, and there are only so many ways that two straight lines can intersect. But if one of the graphs is not a straight line, then that opens up more possibilities in terms of the number of points of intersection. And we're still interpreting solutions of the system as points of intersection of the graphs, just as we did with linear systems. Nonlinear systems may, as was the case with linear systems, be solved using either substitution or addition. Whereas we might prefer the addition method for linear systems, we tend to prefer the substitution method for nonlinear systems. However, I will show you one example where we can solve addition, we can use addition rather to solve a nonlinear system. So you do have some flexibility in the algebraic method that you use in solving a nonlinear system. Let's look at example 1 now. Solve the nonlinear system and sketch its graph. If you look at this system of two equations and two unknowns, the first equation in the system is linear. X plus 2y equals 0. Notice you have x and y in separate terms. Both are raised to the first power. So that is indicative of a linear equation in two variables. The second equation, however, is nonlinear. And that's due to the presence of this x squared term. So because one of the two equations is nonlinear, the system is, as a whole, is classified as a nonlinear system. Let's actually begin with the graph of the system. We're going to graph each equation in turn. For the linear equation, we know that the graph is a straight line. If we take x plus 2y equals 0 and solve for y, it becomes y equals minus 1/2 x. So we would identify that as a line through the origin with a slope of negative 1/2. So the line would pass through the origin, and then if we apply rise over run, from that point, if we go 2 units to the right and down 1, we get an additional point, and we can repeat that as many times as we wish to find additional points on the line. I can go in both directions here. So the line passes through this collection of points. So I've sketched a line through the collection of points I plotted, and now I have an idea of what the graph of the linear equation looks like. So what about the nonlinear equation? Well, if we take x squared minus y equals 5, and solve it for y. You can check this. You should get y equals x squared minus 5. Now, as I said, the linear system is, or excuse me, the linear equation is a line. The nonlinear equation, its graph, we should recognize is a parabola, given the fact that when we solve for y, we have a quadratic function. So some of the key points for the parabola would include its vertex. If we treat this as a translation of y equals x squared minus 5, shifted down 5 units, the vertex would be at 0, negative 5. The parabola should be opening upwards, since we have the coefficient of x squared is positive. Some additional points we could plot without me creating a table here would include 1, negative 4, 1, negative 4, negative 1, negative 4. When x is 2, we would get negative 1, which just so happens to be a point on the line, which would indicate that that point is at 2, negative 1 is going to be one of the solutions of our system, being a point of intersection. Another point we would obtain would be negative 2, negative 1. And then finally, one more pair of points. If x is 3, then y is 4. So we'd have the point 3, 4 and negative 3, 4. So now you can see I've graphed a parabola through the second collection of points, and upon graphing the parabola, we can see that the line in the parabola would intersect twice. Let's label this first point of intersection as A over here in the fourth quadrant, and in the second quadrant we have another point of intersection which we will label B. Now the coordinates of point A are quite obvious. That would be 2, negative 1. So just from graphing, we can identify one of the what appear to be two solutions of this nonlinear system. However, the second point, B, it's not obvious at all looking at the graph what the actual coordinates of that point might be. So the only way we're going to determine the coordinates of solution B will be to solve the system algebraically. So that's going to be the next thing we're going to attempt to do. And in fact, the algebraic method will give us both solutions A and B, and actually allows us to solve the system without necessarily looking at the graph first, although it is helpful to be able to see the graph to understand why the solutions turn out to be what they are. So usually we want to have an algebraic approach to solving a system of equations, whether it's linear or nonlinear. The graphical approach is mainly to give us a visual sense of what's going on and the number of solutions we might expect. So there are several methods we could use, several approaches we could use in solving this particular system. I'm going to choose to use the substitution method. You notice that for the quadratic function y equals x squared minus 5, we have that equation solved for y. So what I'm going to choose to do is to basically pair the equations as x plus 2y equals 0, and I'll write the second equation as y equals x squared minus 5. And then what I'll do is replace the y in the first equation with x squared minus 5, substituting for y and eliminating y from the first equation. So if we do that here, we'll get x plus 2, and then we're going to replace y with x squared minus 5, and then set that equal to 0. So I'm essentially working with that top equation, the linear equation, but I'm substituting the second equation into the first equation by substituting for y. That eliminates y then from the first equation. Okay, if we distribute the 2, we would obtain x plus 2x squared minus 10 equals 0. And rearranging terms, we obtain 2x squared plus x minus 10 equals 0. We should recognize this now as a quadratic equation in x, and we can solve this quadratic by factoring or using the quadratic formula. If it's possible to factor, that should be easier. So let's see if we can't factor this polynomial. If we choose positive 5 here and let's see. Well, let me go ahead and complete what I was going to do. And we see, for example, I could try this, but it doesn't work. Okay, that's what I was just realizing. You get, if you look at the outer and inner products, you get 10x and minus 2x. That doesn't give you 1x for your middle coefficient here. So I need to just erase those. Bear with me a moment. Yes, so if I put minus 2 here and plus 5 here and check by FOIL, the outer product is negative 4x, the inner is positive 5x, and that would give you a middle term of plus 1x. So a little trial and error required. Sometimes there's an error before you get it right. In any event, we've successfully factored the polynomial. Then if we set the factors equal to 0, and solve for x, our first solution would be negative 5/2, and our second solution would be x equals 2. Then we can substitute back into, let's use y equals x squared minus 5 again, and find the y coordinate corresponding to each of these x's. So when x is equal to 2, using y equals x squared minus 5, we get y equals 2 squared minus 5, or 4 minus 5, or negative 1. If we substitute in x equals negative 5/2, we obtain y equals negative 5/2 squared minus 5. That would be 25/4, and I'm going to write 5 as 20/4, and subtracting we get 5/4. So this gives us our two ordered pair solutions. For point A, we have the ordered pair 2, negative 1. For point B, we have the ordered pair negative 5/2, 5/4. Now, negative 5/2 in decimal form is negative 2.5, and 5/4 in decimal form is 1.25. Now, there's nothing wrong with the writing it as fractions. In fact, maybe that's better, but by writing it in decimal form, we can see by looking at the graph that those coordinates do appear to be correct. The x-coordinate should be at about negative 2.5, the y-coordinate at 1.25, 1.25, and that corresponds with the solution B that we see on the graph. So we obtain both solutions of the system by solving it algebraically using the substitution method. We'll continue with the section 8.4 notes in the next video.